Aerogel is an excellent thermal insulator. So far, however, it has mainly been used on a large scale. For example, in environmental technology, in physical experiments, or in industrial catalysis. EMPA researchers have now succeeded in making aerogels accessible to microelectronics and precision engineering. An article in the latest issue of the scientific journal Nature shows how 3D printed parts made of silica aerogels and silica composite materials can be manufactured with high precision. This opens up numerous new application possibilities in the high-tech industry, for example in microelectronics, robotics, biotechnology and sensor technology. Silica aerogels are light, porous foams that provide excellent thermal insulation. In practice, they are also known for their brittle behavior, which is why they are usually reinforced with fibers or with organic or biopolymers for large-scale applications. Due to their brittle fracture behavior, it is also not possible to saw or mill small pieces out of a larger aerogel block. Directly solidifying the gel in miniaturized molds is also not reliable, which results in high scrap rates. This is why aerogels have hardly been usable for small-scale applications. The EMPA researchers have now succeeded in producing stable, well-shaped microstructures from silica aerogel by using a 3D printer. The printed structures can be as thin as a tenth of a millimeter. The thermal conductivity of the silica aerogel is only half that of polystyrene and even significantly less than that of a non-moving layer of air. At the same time, the novel printed silica aerogel has even better mechanical properties and can even be drilled and milled. This opens up completely new possibilities for the post-processing of 3D printed aerogel moldings. With a method for which a patent application has now been filed, it is possible to precisely adjust the flow and solidification properties of the silica ink from which the aerogel is later produced, so that both self-supporting structures and wafer-thin membranes can be printed. As an example of overhanging structures, the researchers printed leaves and blossoms of a lotus flower. The test object floats on the water surface due to the hydrophobic properties and low density of the silica aerogel, just like its natural model. The new technology also makes it possible for the first time to print complex 3D multimaterial microstructures. With such structures, it is now comparatively trivial to thermally insulate even the smallest electronic components from each other. The researchers were able to demonstrate the thermal shielding of a temperature-sensitive component and the thermal management of a local hotspot in an impressive way. Another possible application is the shielding of heat sources inside medical implants, which should not exceed a surface temperature of 37 degrees in order to protect body tissue. 3D printing allows multi-layer and multi-material combinations to be produced much more reliably and reproducibly. Novel aerogel fine structures become feasible and open up new technical solutions. Using a printed aerogel membrane, the researchers constructed a thermomolecular gas pump. This permutation pump manages without any moving parts at all and is also known to the technical community as Knudsen pump, named after the Danish physicist Martin Knudsen. The principle of operation is based on the restricted gas transport in a network of nanoscale pores or one-dimensional channels of which the walls are hot at one end and cold at the other. The team built such a pump from aerogel, which was doped on one side with black manganese oxide nanoparticles. When this pump is placed under a light source, it becomes warm on the dark side and starts to pump gases or solvent vapors.